I'm going to talk about symplectic varieties. And in this talk, I'm mainly interested in affine symplectic varieties. Such variety plays very important role in the algebraic geometry, also in geometric representation theory. And my main result is to characterize nilpotent varieties among such affine symplectic varieties. So let's start with the definition of symplectic variety. So the definition of symplectic variety. In this talk, I will treat such a variety. Let X be normal complex variety over C is called a symplectic variety. If the following holds, so X is a normal complex variety, so X has singularities. So first of all, the regular part, X leg, this is the smooth part of X, admits some holomorphic symplectic two form, say omega. This means that the dimension of X is even dimension, and this means that the wedge of omega, n times wedge of omega, it's a holomorphic volume form, is nowhere vanishing, and declosed. This is the meaning of holomorphic symplectic. This is, of course, holomorphic. And the second condition will assure that X has some sort of mild singularities. So this omega extends to a homomorphic two form on the resolution of X. This means the following. If you this has singularities, so you take some resolution, and then we call this map F. This is the resolution. So you have holomorphic symplectic two form here, and if you pull back this omega to X tilde by F, you get if you pull back this omega, then you have the symplectic form. You have a two form here, and this is a Zariski open in X tilde, and the complement is just some exceptional locus, and this holomorphic two form extend on wall X tilde. This is the condition of the second condition. Then the second condition means that X is rational, has rational Golenstein singularity. This is a remark. And this condition is a very, very strong condition. So so I'm interested in affine case. So I will give you some examples. The first example is nilpotent orbit closure. Nilpotent orbit closure. What does it mean? So if you start with some complex semisimple Lie algebra, okay, and now G is an adjoint group of such a Lie algebra, this means that the Lie algebra of G is nothing but K. Yes. Then G acts on K in the adjoint way. We call it adjoint action. So, for example, the situation is this. For example, S, L, and C. This is a trace-free matrix of n times n matrix. And S, L, and C, this is a matrix of determinant 1. Just act on this space. If you take A, and if you take X, then the action is given by this A inverse. This is the adjoint action, for example. Yes. So you can consider the orbits of such action. So let us consider one orbit. So this orbit is called nilpotent. O is nilpotent if it consists of nilpotent elements. Of course, if it contains one nilpotent element, then every element in O should be nilpotent by the adjoint action. Yes. So there exists, if it consists of nilpotent elements. Okay. So we assume this is a nilpotent orbit. Yes. We take some nilpotent orbit and take its closure inside K. This is the closure of the orbit. Then, before this, of course, this is a homogeneous variety, so this is non-singular, yes? But it admits a natural symplectic structure. It is called the constant Kirillov two-form. I want to explain this. So if you take a point from O, yes, and then it can be identified with G mod G alpha. G alpha is the stabilizer group of alpha. This is the element of G. This action adjoint action of G on alpha, stabilize alpha. This is a stabilizer group. This is a closed subgroup of G, and G mod G alpha is isomorphic to O. Yes. Here, so take tangent space at alpha. It is naturally identified with the tangent space of G mod tangent space G alpha. So this is nothing but K, and this is nothing but K alpha. K alpha is a Lie algebra of this, and this is nothing but the element that X alpha is 0. So the tangent space of O at alpha is identified with such a quotient space. So how to define a symplectic form on such space? This is a vector space. So let us consider the following bilinear map defined by. So now, this is a semisimple. So you have a killing form. This is non-degenerate symmetric form, symmetric bilinear form. This is a killing form. Killing form. So by using this killing form, I define the following bilinear map. So this is the, if you take X, Y here, then this map sends this element to K alpha XY. Yes. This is the Lie bracket of X1, Y, and alpha is nothing but this. Alpha is an element of K, of course. So this is well defined, but it induces a natural pairing on this space, this quotient space. So because if you have this is for example, if you take the element from gay alpha, for example beta, and we call this omega, then what is the beta z? Z is some k, okay, y. And assume this x is assume if x is contained k alpha and y is arbitrary element, okay? Then what happened? Then this should be this. This is the definition, of course, but the property of Killing form, you have this, yes, and but x is inside k alpha, so this should be 0 because of this, so this is 0. So by this property, this by linear pairing, this pairing descends to the pairing on this quotient space. So we call this map omega alpha. Then omega alpha patching together, these omega alpha patch together and gives this is of course by definition this is a skew symmetric form, and moreover this is non-degenerate, and by this assumption, by this definition, this should be non-degenerate. So this gives a non-degenerate 2 form, and this gives defines is a non-degenerate 2 form. But this is, one can check that it is declosed by using the Jacobi identity of the Lie algebra. So this is the holomorphic symplectic 2 form on O. And we call this Kostant-Kirillov 2 form. So O is a smooth symplectic variety in a sense. But O is not affine because and take its closure inside K, then this is a nilpotent orbit closure. But you have, it's not necessarily normal, so you take normalization. This is normalization. And if you have, here you have omega kk, the Kostant-Kirillov 2 form. And this constant, this nu doesn't change the smooth part of O bar. O is nothing but the smooth part of O bar. And you have, here you have omega kk. So the pair omega kk is, one can check that this is a affine symplectic variety. And this is a typical example of symplectic, affine symplectic varieties. And moreover, and other examples. And here we define the nilpotent variety, which plays a main role in this talk. So definition, this is a nilpotent variety. A nilpotent variety is nothing but the set of all nilpotent elements in G. G, let us start with complex semisimple Lie algebra, and N is nothing but the set of all nilpotent elements. X is nilpotent. a priori it's a set, but it admits some algebraic, it carries algebraic structure, and it becomes a normal. We need some proof for normality, but it becomes normal of algebraic variety. Of course, it is affine. Yes, this is called nilpotent variety. Now, important fact is that it becomes a symplectic variety because n has the following properties. Because n is a set of all nilpotent elements, so n consists of some number of nilpotent orbits, or it's this joint union of all nilpotent orbits. So you have nilpotent, so many nilpotent orbits, but such nilpotent orbits, there are only finite number of nilpotent orbits. So we have this as some stratification into this joint union of nilpotent orbit like this. The smallest nilpotent orbit is nothing but the origin itself, and this is the largest nilpotent orbit, and it is called regular nilpotent orbit, and the subregular orbit is the second largest nilpotent orbit. But there are some hierarchies of nilpotent orbits, and the hierarchy is rather complicated, but the largest one and the second largest one exist. And anyway, now n is just a closure of the regular nilpotent orbit. But as I explained, and this is normal, so we don't need to take normalization, and this admits constant Kirillov by using this result. So the n together with constant Kirillov 2 form becomes affine symplectic variety. This is the nilpotent variety. Okay, so of course there are lots of examples of affine symplectic varieties. So other examples include, for example, quotient, symplectic quotient singularities, and some Slowed-Weiss lies. I don't explain this. Slowed-Weiss lies for a nilpotent orbit inside Lie algebra, and Nakajima's quiver varieties. And so on. Such varieties are all nilpotent, all symplectic varieties. And there are lots of examples. So the purpose of this talk.
These are all nilpotent varieties. Is this other example?
No. These are not nilpotent orbits. Some of them are nilpotent orbits, but usually they are not. These are different kind of symplectic varieties. There are lots of other examples from nilpotent orbits.
But when you construct a symplectic structure to nilpotent, where you use the condition of nilpotent?
Usually, essentially the nilpotent case is important, because if you take, for example, of course, if you start with arbitrary adjoint orbit, you can equip a symplectic structure. But usually if you start with a semi-simple element instead of a nilpotent element, then the O is just O bar, and this has no singularities, and it's something like just a usual symplectic manifold. So the interesting case is just a nilpotent case. And from the point of view representation theory, the nilpotent case is the most interesting case. So basically, the nilpotent orbit is a product of semisimple one and nilpotent one. And semisimple one is smooth one. So the difficult part is nilpotent.
The orbit of semisimple one is also symplectic variety.
Yes, yes.
For the quiver varieties, do you have some restriction on the quiver?
Yes, sometimes, but I don't mention about that. My purpose is just maybe I have, but I'm not so familiar with the quiver varieties. But maybe some restrictions. Of course, the purpose is give a characterization of such a nilpotent variety with constant killing of two form among symplectic, affine symplectic varieties. This is the purpose of this lecture. So the main result is this. So the situation is this. So we assume the following. Now x omega satisfy the following. First of all, x is affine. Affine. This is a symplectic variety. Sorry. This is assumed. X is defined as a complete intersection. X has dimension 2n, and X is realized as a complete intersection of homogeneous polynomials. So X is defined as we call this the coordinate z1 to z2n plus r. 2n plus r. And X is defined as the common zeros of homogeneous polynomials fi. So fr is 0. So fi are all homogeneous. So it is a complete intersection singularities. And we assume that this is affine. This is a symplectic varieties, and omega is a symplectic tooth. This is a symplectic variety, and assume that omega is homogeneous. So it has a natural sister action. The natural sister action is given by, if you take a point z1 to zn plus r, then this is nothing but the usual one. You have a natural sister action because fi are all homogeneous. And the second condition is omega is homogeneous with respect to this action. That means if you take this sister action gives automorphism of X, and if you take omega and pull back this omega, then you have a new symplectic 2 form on the regular part. But this pullback of the symplectic form can be written as some TL times omega. This is a scalar multiplications, and L is some elements. L is some integer. This is the assumption. We call this assumption a star. So the example of symplectic variety satisfying this condition is nothing but nilpotent variety. So what is nilpotent variety can be realized as follows. If you start with semisimple Lie algebra K, and you have a joint action, then you can take a quotient. This is nothing but a GID quotient. This is spectrum of the ring of regular function on K invariant by G. So this is the K, K, G. This is the invariant function on K, G invariant function on K. And it is nothing but there is some invariant function here, some invariant function. It is homogeneous, and it is generated by something like this. And this is algebraic independent, so this is nothing but the CR. You take 0, the origin, and we call this map a joint quotient map chi. And if you take null fiber, a central fiber of chi over 0, this is nothing but n. Yes. The easiest example is this. If you start with SLN, then this R is nothing but n minus 1, and this map is given by the following. If you take A and you consider the characteristic polynomial of A and expand it as a polynomial of T, and this is Tn plus some A n plus 1, something like that, Cna. But A is trace-free, so this part is 0. So this is nothing but map associated to A, the Ca2 to Cna. So, and what is the nilpotent matrix? Nilpotent matrix is a matrix such that the characteristic polynomial is just a Tn. Yes. So it is nothing but chi inverse 0 is nothing but the set of all nilpotent elements. So this is the easiest example of this situation. But here, this is a symplectic varieties. But n is in this case, n defined as a complete intersection like that. And this is the C. If this has a dimension 2n, then this has dimension 2n plus r. So this is nothing but, this is inside C 2n plus r. So this situation realized. So the nilpotent variety satisfies this assumption. So the main result is that if this holds for general affine symplectic variety satisfy this condition, then it should be this. So the main theorem is if x omega satisfies star, then x omega should be a nilpotent variety for some simple Lie algebra. This is the main result. So n omega k, the constant Kirillov. So I want to explain this in the series of lectures. Yes, this is the main purpose of this lecture. Okay, so this is an overview of this lecture. So to prove this, I will use many theories. For example, contact geometry and Mori theory and the Poisson deformations and representation theory and so on. So I want to prepare some of these matters. So first we start with contact structure. So contact geometry. So what is the contact structure? As you know, symplectic structure is closely related with symplectic structure. Symplectic structure is related with contact structure. And I want to explain the relationship between the symplectic structure and the contact structure. So if you start with such a variety with symplectic structure, then we get some another variety with contact structure, and we look at such a variety with contact structure, and then get some result by using Mori theory, and we have some results. So we start with contact structure. What is contact structure? For example, you can consult with Arnold's book on mechanics. But what is the contact structure? If you start with M, the complex manifold of odd dimension, so this is a complex manifold of odd dimension 2n minus 1, then contact structure on M is nothing but the following exact sequence. Here you have a tangent bundle. This is a vector bundle of rank 2n minus 1. And exact sequence consists of the following one. Here, this is a line bundle. And this is the tangent bundle. And this is a kernel of this map. And this is the exact sequence of vector bundle such that the following property holds. So, such that the following holds. You have a skew symmetric pair. You have some bilinear pairing induced by exact sequence. This is f times 2 f to L. It is defined like this: x and y. X and y is a local section of this vector bundle. So it is considered as, it is regarded as some vector fields on M. And so x and y are vector fields on M. And take its Lie bracket, take its bracket of as vector fields. If you have two vector fields, you get x, y bracket. A new vector field, and new vector field, you have a new vector field here. Then you send this xy to by this theta. So this theta. So you have a natural skew symmetric form. This is the condition is that this is a non-degenerate pairing. This is the even dimensional This is the vector bundle of even rank, so it has some possibility to that it's non-degenerate. Yes, this is the contact structure, and this theta is nothing but the section of twisted one form, m omega 1 to 10th right with L. This is the twisted one form. This one form is called contact form. And this L called contact line bundle. Okay, this is the contact structure. What is the meaning of contact structure? This is not so obvious, because, for example, if you have some m to some fibration to one-dimensional varieties, this is some one-dimensional varieties, and if you have a foliation, and you take if you have such a situation, you get some sublime bundle of theta m of corank 1 as a fiber directions. But in such a case, this should be 0. So in that case, the subbundle correspond to the fiber is integrable. Integrable means it is closed under the bracket. So this should be 0. So this means that f is highly non-integrable. This means that f is highly non-integrable. So it doesn't come from any such a fibrations, such a foliations. So it is highly non-integrable. This is the meaning of the contact structure. So now we introduce some proposition. The proposition. First proposition is this. So let us, if this is the dimension, and if n is 1, there are nothing to do. So we only consider the n is bigger than 1, and let m be a complex manifold of dimension 2n minus 1. So if you start with this, and theta, assume theta is some twisted one form, and L is some line bundle, holomorphic line bundle, and this is a twisted one form, not necessarily contact form. And then we have the following properties. First, d theta wedge. This is the n minus 1 times wedge of d theta. Wedge theta. Notice that this is not well defined because this is twisted. So this is not well defined, usually. Because, of course, if this is not, it's okay. But if you twist it, it is not well defined. But this is a 2n minus 1 form. This is a well defined as an element of m 2n minus 1 times ln. Is well defined. Well defined. And second, the following equivalent. Following equivalent. A. This theta gives a contact structure. Theta gives contact structure like this. Contact structure. And B. This is a nowhere vanishing section, which this is a nowhere vanishing section of this vector bundles. So this is the equivalent. Just a moment. Yes. So I want to explain this. So how to prove this? The first is the proof of this, the first part. This is a very easy because if you cover, first you cover M by some open set such that LUI are trivialized. Yes. And you have a transition function. GIG is a transition function of L. Then, you have a section here, and you have a section theta I here by using this identification. Then theta I are glued together like this, GIG, GJ. Yes, this is almost definition. So, what is this? What is this? This is the. Now let us consider this element. So this theta I wedge n minus theta I. So what is this? This can be written as follows. This is Gij d Gij theta j n minus 1 wedge Gij theta I. Sorry, J. Sorry, J. This is J, yes. And we expand this. And this is nothing but n minus 1 d theta j and Gij n minus 2 theta j 2 and something and something and something and Gij theta j. But here you have theta j, but this term, the remaining terms of here, this is the exception, but the remaining terms always contain some theta j, but theta j wedge theta j is 0. So theta j wedge theta j is 0. So this implies that the Gij n minus 1 theta j, sorry, this is the, this is the, sorry, n minus, sorry, this is something, just a moment, just something is Gijd, sorry, this is the, I think this is Gij d theta j plus dgij theta j n minus 1 Gij theta j. Yes, this just expand this and expand this. Then we have Gij, this is n minus 1 d j n minus 1 plus this times n minus 2 dj n minus 2 dgij theta j and so on, and this Gij theta j. But here such terms always contains some theta j. So theta j wedge theta j is always 0. So this vanish. So we have Gij n minus 1 and this, so Gij n this j n minus 1 theta j. So it has a transition function Gij n. So this means this. Yes. So this is a well-defined element. This is the first part.
This double sum, right? This double sum for j, like y separate only for separated. So here summation for j, the right term is summation for j, right? Both summation for j, right? I is fixed.
Summation of what?
Summation for j, right?
Are we using the Einstein convention or just
Is it something?
No, he just considered each second the sum.
This is just the expansion. This is just the. This is this. This is sum. Okay. So this part always contains such a theta j, and here you have theta j. Then this vanish. So such terms vanish. This term vanish, and you get this jij and this and this. Yeah. Okay. It's not summation. This is just a transition function. Yeah. This is just a multiplication. Okay. Okay. This is not sigma. Okay. This is almost the definition of this. Yeah. So the second part is the important part. So if theta gives a contact structure, then how we prove this? So if theta gives a contact structure, then we have a following exact sequence: theta m to L, and this is surjective. By the definition, this is surjective. And you take a kernel of theta. We call this is f. Yes. And take any point. Take arbitrary point p from M. And let us consider the fiber of such a vector bundle. Then we have a following surjective map. This is a one-dimensional vector space, and this is the n minus one-dimensional vector space. Here you can take v, some vector v, in such a way that this theta v is not zero because it is surjective. You can choose such things, and you can choose some basis of this vector space, w1 to w2n minus 2. Then theta mp is as a vector space generated by 2n minus 1 element, w1 to w2n minus 2v. This is a basis of the vector space, right? So, and let us consider the following things. Yes, this one. I want to prove that A to B. The proof. So if theta gives a contact structure, then we get some exact sequence and take such things. And now I want to show this. And so you consider the following element here, 2n minus 2v. Yes. Then what happens? But it's important that theta wi is always 0 for every I, because this is a kernel. So theta wi is 0. So theta wi is always 0. So this is nothing but this 2n 2 with theta v. Yes. Other part vanish because of this. Then this is of course 0. No, not 0 by the definition. But what is this? Here the contact structure comes. So the condition of the contact structure is this: f times f to L. This is given by xy to theta xy. Here, let us consider this is the local. This is the local condition. So this is just take some small open neighborhood and restrict it, and this can be regarded as a trivial one. So theta is just one form, and d theta xy is by definition of d, the derivation, x theta y, this minus y theta x minus theta xy. Yes, but here x is a local section of f, and theta is here, so this is 0, and this is 0. So this is theta xy. Yeah. So this is non-degenerate by the assumption. The minus sign, we don't care minus sign, but anyway, this is non-degenerate by the assumption of contact structure. This is non-degenerate. This means that this is non-degenerate. This means that df is non-degenerate. So this non-degenerate means that this is not 0. Yes? So this is not 0. So this is not 0. So this is nowhere vanishing. So this is nowhere vanishing. And we proved that this is nothing but the condition B. Right? So the converse is almost the same. For example, if you start with B, what is the condition B? B is just this is nowhere vanishing. Nowhere vanishing. Yes. And the first, I want to show that theta is surjective. First, I claim that this is a surjective. How to prove this? If theta is not surjective, if not, then there is some point M such that the theta MP to LP, this theta is 0 map. This is one-dimensional and it's not surjective, then this is automatically 0 map. And if such things, all elements here, it goes to 0 by theta. So this should be, here you have theta, and so this is 0. This is 0, because for every v, theta v is 0, and you have here theta. So if you restrict this form to p, then it is 0. But this is nowhere vanishing, so contradiction. So this is surjective. This is first. So if theta is surjective, then for every point p, theta mp, you have the following exact sequence as follows. Fp, yes. And then the same argument shows that this is the same. This is D. This is nowhere vanishing. This is nowhere vanishing if and only if d theta f is non-degenerate. D theta f is non-degenerate. And by using this formula, this implies that this is theta f times 2f to L is non-degenerate. Non-degenerate. This is the same. So this is surjective, and this is non-degenerate. So theta gives a contact structure. contact structure. So this gives the equivalence of A and B. Okay, and B as a corollary of B, the corollary, if B holds, then this means that this is nowhere vanishing section of M times n to n minus 1 Ln. Yeah, this is nowhere vanishing. Nowhere vanishing. And what does it mean? This is a trivial. This is a trivial line bundle. Then this is a trivial line bundle. This is trivial. So it implies that this is a canonical bundle. This is a dimension of M is 2n minus 1. So this is nothing but this. So we have a corollary that corollary. So if M is a contact manifold, so complex manifold with contact structure, then the canonical line bundle is this, should be this. This is the important corollary. So, and let us give some example of contact structure. This is a fairly easy example, but I want to, for example, if you start with Cn minus 1, this is the odd dimensional space, and take its local coordinate in such a way to n minus 1, y n minus 1, z. And if it take theta to be the such form, yi dy dxi, and I goes run through 1 to n minus 1 plus dz. This is a one form, and this is a Stein space and a affine space, and all line boundary is trivial. So the twisted is necessary, and this gives theta gives contact structure. This is called the standard form of contact structure, and if complex manifold admits contact structure, then every contact structure can be written as following form locally. So this is called the standard form of contact structure. So the contact structure on global manifold is nothing but gluing such a one form by twisting. So this is the contact structure on complex manifold. So let's finish the first lecture, and I will explain the relationship with symplectic structure in the second lecture. Yes, I will finish this.